for joining us for the webinar today entitled Smoke Suppression in Phenolic Urethane Bonded Sand Systems Through the Use of Engineered Sand Additives. A few things to know through the webinar. Due to data protection policies, your first and last name will not be visible, nor will any pictures or your camera if you have one. Questions will be available via the chat function. The Q&A mode is active. If you'd like to post a question, we will answer it throughout the webinar. A recorded version will be made available. If you signed up for the webinar, it will be emailed to you within a day or so, and it will also be available on ASK's internet. Our presenter today is Dr. Paula Vivas. She's the R&D manager for coatings, sand additives, auxiliaries, and feeding systems. She's been with ASK Chemicals for 7 years now. I am going to be moderating the webinar. My name is Stacy Clifford, and I am the technical product manager for coatings, sand additives, and auxiliaries for ASK Chemicals. I've been with ASK going on 25 years. And now I will hand it over to Paula.
Hello all, and good morning to some of you, maybe good afternoon for some other ones. And thank you, Stacy, for such a nice introduction. So today we're going to start with the outline of the talk. I divided this talk in 5 sessions. First, we'll do an introduction about the mold and core making technology and overall the casting process. After that, I'll discuss the motivation, why we did this project, and then followed by how we did the characterization of the sand additive, the experimental approach, and some data that I will be sharing with you. We will also review as a sand additive effects of this sand additive could have in the phenolic urethane core properties, and we'll finish with the summary. So let's start talking about mold and core making. So we all know that in order to have good quality castings, we need to make good molds and cores. It's very critical. For that reason, we had to find ways to create these molds and cores that can serve that purpose. And for that, well, most foundries use silica sand as a media. We're not going to go in all the possibilities that could be, but let's say we want to bind these sand grains together. So we had different ways to do it, and then going to go over this summary here. So the main categories that I will say that are out there and the mechanisms to bind sand together are the green sand and the chemical bonded sand. We had other systems like loose foam and unbonded loose sand, but the most common are chemical bonded and green sand. Now inside the chemical bonded sand technology, we have another subcategory, which is the organic binder systems and the inorganic. Now, for the purpose of this talk, we're going to mainly focus on the organic binders. And the organic binders also have different subfamilies, as I'm showing here. Now, what you can see is that most of them actually are differentiated by the way you cure your resin system, right? So, but for the purpose of today, we are going to focus on the phenolic urethane Novec technology. And in general, phenolic urethane binder systems are excellent choice for foundry and mold core making, as you're probably familiar with them. I'm going to mention some of the advantages of the phenolic urethane. We have the high productivity you can accomplish. We can use them on low levels, so the resin can be used in low level addition, and at the same time, you can accomplish very high tensile strength. They're also very good for making complex geometries. So when we had those complex shapes that need to be designed, this binder system serves this purpose really well. Also for surface finish of the mold, I think they're wonderful for that kind of uh, property. And we also have we can achieve high tolerance using these binder systems. Now, when we take those molds and core make with phenolic urethane now to the casting process, right? When we're ready to pour the molten metal. Well, the phenolic urethane will be exposed to very high temperature due to contact with the molten metal. And when they are exposed to very high temperatures, they undergo uh, thermal decomposition, so they get pyrolyzed, and that as a result of that, there's an undesired smoke and emissions. There's been a lot of work, especially for ASK had done on the formulations of PEP SET systems, which is kind of how we refer as phenolic urethane Novec system, our PEP SET systems, on improving this situation with the smoke and emissions. I mean, reformulating has been a big thing, and I think we had gotten some significant progress in some of our binder systems to eliminate some of that smoke and undesired emissions. But still, we have some more work to do, and we keep improving. We want to go toward cleaner technologies every day. That's kind of ASK mission. And for that, that will take us to the motivation of this talk today. The idea is to have to use an engineer's SAN additive. So SAN additives are used in most foundries for controlling casting defects. So this time, the idea is to have this SAN additive serving a dual purpose. So in addition to the high quality casting and eliminating casting defects, we will be able to reduce the smoke. And for the rest of the talk, you probably hear me saying the word DISA. This means dual engineers and additive. I will refer to this proprietary blend of SK that we'll discuss here as a maybe BLM SK later on. So that's just the way we refer sometimes internally and sometimes in the lab. This engineer blend had now been is patent pending. So let's walk through for the rest of the talk on how we develop this SAN additive. So first we had to do some bench work. So in our R&D, we just developed a small course, and it's a simple concept. We just like making a mold or a core in an actual foundry. We take the silica sand, we mix it with the SAN additive. I always actually suggest this to people. So you had to be sure the SAN additive is completely mixed with the silica sand before you add your phenolic urethane binder system. The phenolic urethane Novec binder system has three parts. There is a phenolic resin, then the polyisocyanate, and then we have the amine catalyst. In this case, it's a liquid amine catalyst, which will be used to control the speed of the reaction. The result of that is a urethane bond. That's when you cross-link the polymer. So you form a very nice mold core. Just to show below some examples of the small specimens we use in the lab, so people are familiar with the dog bones. We can make dog bones at different conditions. Always, of course, we use a control specimen, which is the one with no additive, and then we can change the level of the additive to 2, 4, 6%. And later on, I will show why we use certain particular range for this SAN additive. So here's the first example, the first observation working with this engineer blend. So if we want to look at how much smoke we are producing, the first experiment you will do in the lab will be to pyrolyze the cores. So we use a muffled furnace. We place the cores around 700, 750 Celsius for about a minute. Then you take that core and you can place it in a ceramic bench in a platform. And as you can see on these two photos, this is actually photos from a video that we made. On the left side, you see the no additive. We try to help the eye by putting a black background and a ruler. And you can see that the no additive shows significant amount of smoke. And on the right side, we have our dual engineer sun additive at 4%. And it's not completely 100% smoke suppression, but definitely is a significant amount of suppression of the smoke in the presence of this sun additive. Now, of course, we needed to do something a little more fancy than just looking at the black background and a ruler. So we wanted to quantify the smoke. And the way we do it, so we use the same approach. We take the pyrolyzed cores, but now we transfer them to a chamber. So I show here in the middle of the pictures, you can see the actual experimental setup. This experimental setup is a vertical step. Uh, you have a light source and a photodetector facing each other. And when the smoke, due to the core present, start traveling upwards, you will see that the incident light will be scattered by the particles and anything that will be blocking, the incident light. For that reason, then you will have like a physics concept, you will have scatter light, and which is what will indicate the amount of smoke present in the in the experiment. So when you're going to record this, you will measure the intensity of the scatter light as a function of time. So that means this blue curve here, just a cartoon to understand the data. The blue curve means you have a core specimen that had higher smoke, and then the orange curve means less smoke. That's the kind of data that we'll generate from these experiments. So let's look at some real data. So we analyze 4 samples. So we measure 4 samples here. I actually showing the picture of each of the pyrolyzed dog bone specimen at different conditions. We have a control sample, which is the no additive. We always have that there for comparison. We have 2 levels for the dual engineer sun additive, DLMSK, 2% and 4%. And we also add a commercial sun additive just to have another comparison point. So as you can see clearly here, as I explained earlier, so if you have a plot of intensity as a function of time, if you take the area under the curve of this, that will be your total smoke. So if you see here, the green and red curve definitely shows some reduction. So if we want to quantify this a little bit easier, you can sum these individual points and get the area under the curve, the total amount, and divide by the intensity as a function of time, sum when in the presence of no additives. When you do the normalization, so you can see at 0%, you had 100% total smoke. As you increase the amount of sun additive, you will see then there is a decrease on that total smoke. So to determine the smoke suppression, you will do 100% minus this number. That will give you your smoke suppression. Now we were very excited here. I mean, this is exactly what we wanted to accomplish. We wanted to have an additive that was going to help to control some of these smoke and emissions. And this bench work was for us very excited. So we wanted to do the real thing, right? So far I show you that we've done everything with little core specimens, pyrolyzed them, and looking at the smoke. So at the ASK, in our R&D team, we have the advantage that we had a pilot foundry lab. So we had a 300-pound induction furnace where we can pour steel and iron, aluminum. So we decided to make some bigger cores on step cones and then pour some steel and look at what we were going to find for the smoke reduction. So you can see their step cones make the darker ones are made with the additive. The light color is the one with no additive. And we place them inside graphite molds. The idea with the graphite mold is that we only see the contribution coming from the core in case we want to determine the smoke and emissions. So we want everything from the core, not the mold. At the moment we were going to make these videos for recording this event, we remove those pudding caps. They get removed immediately since they're made also of PEP sets. So we remove them. Let me show you now a video that we make. And by the way, these cores were made just to make a clear here. They were made with round silica sand, 1.2% PEP set magna, 1215, 2215, and a ratio of 60-40 part 1 to part 2. And the catalyst was 4%, 3401. Let's see if I can play this video. I think, see if this works. So you can see here, I'm not playing the whole video because they're very long, because we're trying to set this up. On the left side, you see the no additive. And on the right side, you see the BLMSK engineers and additive. So I can play it again. So if we went too fast, you can see on the left side, there is a significant amount of smoke when you don't have the additive. And once you place the additive, make the additive in the core, you definitely suppress significantly the amount of smoke. So let's go back to the presentation. Right. All right. Okay, so what you can see, and you just saw in the video, is that clearly there's no question with the additive. We can definitely suppress that quite a bit of smoke there. It took about 8 minutes when we analyzed each of these videos. It took about 8 minutes for the core with no additive to stop smoking, and it took about 3 to 4 minutes for the core actually to stop smoking when in the presence of the additive. So that already give you an idea that what we saw in the lab was pretty in good correlation with what we see actually in the foundry. Now, so far, we had seen the smoke suppression. It works very nicely. Now, the next question that comes to mind is, what are we suppressing? Are we suppressing any of these undesired emissions that we know are there during the casting process, like volatiles or any pollutants? Well, we needed to look at that. So for that, we went back to the lab, took again some of the cores. We make this time, I think, 6 samples, 6 core specimen at different conditions, some with different sand additives, but all of them were made with the same amount of sand additive, 3%, I believe, in this case. The core conditions were also the same as I've been showing so far during this presentation, 1.2% PEP set magna, 60-40, 4% catalyst. And this work actually was in collaboration with our colleagues from SK Germany. They do have a custom built mini hook stack set up. And this experimental setup is very interesting. And instead of what I showed earlier for the smoke, they actually collect the byproduct from the pyrolysis and they transfer it to collection glass tubes. And they take these byproducts and they analyze it in a chromatography instrument. So that really helps to determine what kind of species are living on the smoke. On the plot on the right are the results from the experiment. We have that if you look at the y-axis, which is the species found in milligram per kilogram core weight, you can see that the no additive had the higher emissions. Benzene, toluene, xylene are the BTX, and the naphthalene is what people call polyaromatic hydrocarbons, I believe. That's the naphthalene. And there's a lot of studies already done by different people that show these are the highest species. They are kind of concerning for health issues. They are present on the casting process. So we are excited to show that In the same fashion as the smoke suppression, we are able to reduce some of these emissions with the engineer blend BLMSK. Again, here is ASK additive that we had, the Beno Ultra 350. We currently is a additive we use for steel applications. It's commercial. We had two more commercial additives here, and a typical black iron oxide, just to illustrate where we are with respect to typical additives. So at this point, we had shown we can suppress the smoke, we can suppress and reduce some of the these undesired BTX and naphthalene type of uh, emissions. So we have to answer a different question now. We are developing a SAN additive, and when you're working in developing a SAN additive, especially for us in ASK, we look in details a lot of aspects of this, because when you put a powder that is finer than sand, you need to be careful not interfering with properties like tensile strength, the reaction of the speed of the reaction, and the most important thing also, it needs to serve the purpose of eliminating veining and metal penetration, and in some instances it should help with the surface finish. So independent of the smoke and emissions, it needs these additives that we develop needed to uh, help with this, and kind of so we needed to validate this. So let's look at each of them. So the tensile strength, and this is well known that for most sand additives, because they are finer powders, and they also, the nature of these powders are, they had high surface area, they're fine, is known that they could have a reduction in tensile strength. And so that's why when you develop a sand additive, you had to do quite a bit of homework on trying to adjust the distribution so it's less detrimental to the tensile strength. So let me show you here two different time points for tensile strength. We pick 1 hour and 24 hours. Of course, we can monitor other time points, but just to illustrate here, you can see no additive, and this is sort of cores made with, again, 1.2% magna, 60/40. We have 0% no additive and 3% for the rest of the samples with sun additive. And you can see that we're not surprised about this. There is a reduction on tensile strength from the use of the sun additive at 3%. But the way we recover our tensile strength is by adjusting the catalyst to a different catalyst with maybe higher active ingredients. So that we have now 3501 here, and then we already kind of back into where we want to be. Remember, these tensile experiments are probably 20%. So we were very pleased to be able to recover the tensile strength of the core without had to increase the binder level. And what I want saying this, because if you think about it, if we had to increase the binder, we had to have kind of more like a chicken egg situation, where more binder, then more smoke, and then more additive, and then reduction of the tensile strength. So we don't want to fall in that cycle. So the idea is that we can recover the tensile strength by just adjusting the catalyst or the type of catalyst. And we also found some catalysts that didn't work very well. So uh, if we do this in some customer or facility, we will have to work closely to determine the most ideal conditions for catalyst and binder to get the best of we can obtain. Now let's look at the speed of the reaction. So in a PEP SET system or phenolurethane novate, these are two aspects that I think are very important. So when you mix your sand with your binder, you're gonna have you're gonna have certain time where you can mix, you can work with the aggregate, but it's gonna start curing, it's gonna start hardening. So we have 2 points in time, which is what people define as the work time, and that will be the amount of time available to work with the sand aggregate before start hardening. So you don't want to get there. You want to try to work before that time and make hand run your sand or whatever you're doing. And then after that, once you pass that time, now you had to watch for the strip time, which is the time where you had to achieve certain strength so that you can safely remove your core or mold from the pattern safely. So on the right side again, that's the same condition as I show for tensile strength. For no additive, we're around 6 minutes. So when we put the additive, we and this is what we expected, we were going to slow down the work time. But again, we just adjusted the catalyst to make this work again back. And actually, it was interesting because we didn't change the percentage of the catalyst, and we were able to actually speed up a little bit the work time. So that means we could probably use 2% of this catalyst and get back to where the no additive conditions are. Again, there's some catalysts that we found not very helpful in this case, like the 330 didn't really help here. And the same applies for the strip time, they're kind of correlated. So if you could adjust the work time with a different catalyst, make it work, it's going to work for your strip time. So what's the next feature that the sanity needs to have to be a good sanity, right? Well, the anti-bending functionality needs to be there. So for that, we need to go back to the foundry and lab and do some testing. So we took some of our step cones that we make earlier, but this time we placed them in PEP SET molds and just did a normal pour. And the result of these castings now are showing on the right side. We cut the step cone casting in half, so you can see the inside of the step cone. So for the no additive, we had quite a bit of veining. I mean, it's pretty dirty casting. You don't see in this case, for this particular example I'm showing here, you don't see that much metal penetration, but sometimes we get pretty bad penetration. Um, so in this case, I'm mostly seeing veining, but you can eliminate all of that veining by just adding the 3% BLMSK to an engineers and additive. So that's pretty exciting because so far uh, the conditions for a good sand additive are kind of achieved here. So we're able to clean the castings. So in summary, I will say we had successfully developed a dual engineer sand additive that can have and produce high quality castings. It can reduce the smoke. And on the other hand, the other properties of the phenolic urethane Novec mold and core technology can be adjusted to make this whole process work smoothly and without any issues. So far, the tensors can be adjusted, the reaction speed could be adjusted, the elimination of the veining metal penetration and improved surface finish was accomplished. And more exciting, we had the smoke and addition reduction, which will be the new benefit from the use of this sand additive. Of course, I can finish this talk by acknowledging and giving thanks to the people who work with me really hard on making this project to come to a successful end. We have in my R&D team a lot of good scientists, and especially I want to thank Matthew Schaffner. He did lots of smoke testing and tensor strength. He worked really close with me on this. I want to thank Merrick Simon, who is our technical product manager for Metallurgic. He, beginning of SK, really helped me, along with Glenn, for setting up the foundry testing and smoke suppression in the MAL lab, the metal application lab. And also last, Dr. Wolf Wirth for his support on the BTS emission testing in Germany so that we could characterize that part in the project. and get some idea what we measure in terms of emissions. And with that, I think we can discuss some questions.
Thank you, Paula. It was a very informative talk, and we do have some questions. The first one I think might be better suited for Isabel. I'm not sure if she's able to speak at this time, but the first question is, are the videos available? And I know that we're going to be sending out the webinar to the emails of the participants as well as putting it on ASK's internet. Well, I do not know if the video will be available. So, Isabel?
Yeah, hello everyone. The videos itself will not be available at this time. We are checking in because of this question, if and how we can make them available.
Okay, thank you. The second question, I believe Paula talked about this in her discussion, but maybe she can go over it again. It is, does 4% addition influence the strength of the cores?
Yeah, I mean, one thing I mentioned during the talk is the levels of additives that we'll add depends of your process. So we'll have to find a compromise where we can work and get the best we can get from the sun additive, and also be able to make cores safely with enough tensile strength and good reaction speed.
Thank
I
you,
don't know if that
Paula.
answered the question.
Yes,
Yeah.
yep. Thank you, Paula. The next question is again for Isabel. We're going to be sending the webinar out to your emails, but the question is, will you receive the PowerPoint presentation? I don't believe it's going to be in that form. Isabel, do you know what format it's going to be in?
Yeah, it will be just the video, so the actual PowerPoint presentation, unfortunately, we can't make available, but yeah, you can see all the slides in the recorded version, of course.
Will it be sent out as a PDF?
No, so the video will be as a video format, so something like MP4, and
In
of
the
course you can, so the presentation and the video and the recording, everything in one file.
Okay.
Okay.
We have another question for Paula. Does the term smoke include carbon monoxide?
I think it does. I mean, I think we will have all kind of things on the smoke. We didn't in detail break down everything, but we wanted to focus mostly on the BTX, which are the most harmful. So yeah, it could be that we have some of that.
Okay. The next question is, what effect does the additive have on the core strength as well as work time, strip time? I believe you answered this in your webinar, but maybe you want to go over it again?
Yeah, well, I mean, I can maybe go back to this and show the slide again. Um, we are aware that sun additives will impact core strength, and this is something that if you decide to work with a particular sun additive, you will have to adjust. In some cases, it's necessary to adjust the binder level. Um, um, but in most cases, you probably can also just play with your catalyst or the type of catalyst you use to achieve that tensile strength at the time when you need it. So,
And the next question is, maybe different foundry with different silica sands need different catalysts to adjust strength and other parameters, right? I
right.
believe you answered this.
Yeah. Right.
Yes, that is correct. The next question is this new additive technology as well available outside the US?
Well, I mean, I'm sure it will be. I mean, when the timing comes, I think we'll make the announcement, right? So, yeah,
Right, right
yeah,
now,
yeah, right.
yes, right now it's not available outside the US, but we're hoping that it will be. The next question is, has phenol testing been considered for this product?
Yeah, and that's actually like a second phase of this. I mean, we we started with the BTX, and HAPs, which is the naphthalene that was mostly found. But yeah, we're moving towards also evaluating this other phenol and formaldehyde. Yeah.
Okay, and then the next question is, has this additive been trialed using multiple formulations of PEP SET or different no-bake binders?
Yeah, correct. That's actually something that we have been doing for a while now, is evaluating every single PEPSET system that we have, from the polio-based type PEPSET to quantum magna. Yeah, we're evaluating everything.
Okay. And the next question asks, do we have some real casting application case study? I can answer that. We've only tested this in the lab so far, and we're hoping to get this out in the field before the end of 2021. There's another question about just a very specific no-bake system, the PEP SET X1000, 2000. How does the additive perform with this system?
Well, I'm actually happy. Sorry, I'm losing my voice here. I'm actually happy somebody asked that question, because when we had started this project, we picked that one as a kind of first candidate, and is the one that gets more benefit from all of them. So that's where the sun additive does a better job, I would say.
Okay. Next question, is there a preliminary explanation as to why the catalyst helps improve the SAM mechanicals and the work time strip time?
Well, I mean, we know that the catalyst is what helps to control the reaction. So I think that you know that if you give more energy to the system, you're gonna overcome that barrier and change the reaction. So yeah, I know that increasing the catalyst or changing the amount of active ingredient the catalyst is gonna help with that, right? It's like almost like running a race. If you give people, maybe more caffeine or cheer, then it will get there faster. So yeah.
Okay. Next question is, what is the availability of the product? When can customers test it? How do they order it? How is it packaged? Pricing. Um, this will all be made available when the product goes live, after we've completed our case studies. There'll be an SDS and a technical data sheet, and you can get with your ASK account manager, and they will let you know when it's available to order. The next question is, can you provide details on the sieve distribution of the additive, and how does it compare to Beno Ultra 350 specifically?
Well, I kind of give it a sad distribution, but yeah, it's it has a very nice distribution, like I mentioned in this slide, that is actually here. It's not so fine that will completely kill the tensile, but it's not, we want to have in any sun additive, you want to have a distribution that also is not so coarse, that it help you with metal penetration and improve surface finish. So we have worked on getting tuned this distribution to achieve those goals. Yeah.
Okay. Next question. When you measured the smoke with laser refraction, at what temperature was the core heated?
Um, it was we had a light source and a photo detector. The core gets pyrolyzed in a muffled furnace at around, I believe, 700, 750 Celsius, and then it's transferred into a chamber. So it is around 700 Celsius the beginning, right? But I mean, if you know thermodynamics, it's eventually going to cool off. But yeah, it starts at 700 Celsius.
We have a lot of questions. I'm not sure how much time we have.
Yeah, right.
I'll just keep going. I think we're okay on time for now. The next question is, do you have any data regarding the permeability of the bonded sand with this additive?
Oh, we I believe we have. I don't have it for this presentation, but yeah, we do. This is a part of any kind of sand additive development. We look at the permeability in the presence of the additive and with additives. Yeah.
And the next question, can this be a replacement for other iron oxide products such as Vano Ultra 350?
Well, I mean, Ben Ultra 350 is a great an additive, especially for steel applications. Yeah, I mean, as I say earlier, we keep improving our technologies and coming with a different concept. The Ben Ultra 350 is a really good additive for veining penetration and steel castings. I would say it's, probably not having the same ability to suppress the smoke as the VLMSK, but I mean, yeah, I mean, it could if the idea is for the customer to reduce the smoke and had that benefit, it could potentially work. Yeah.
Yes, I believe so also.
Yeah. Right.
Yes, and in addition to reducing smoke and emissions, it will also produce clean casting. So
Right.
yes,
Yeah.
it should work as a replacement for 350. Next question, how does the additive affect burn on or burn in? I believe you have a casting that shows that.
Yeah, I mean, we didn't show because of time. We had limited amount of time here to show all the studies that we do because we do different kind of geometries and cores. The step count here is mostly kind of to look at the veining. So, but yeah, we definitely eliminate a lot of casting defect related with mold and core making with the additive.
There's a few more questions. Has any hot mechanical testing been done?
Sorry, what was that question?
Has any hot mechanical testing been done?
Not
I, s-
sure what.
I-
Uh,
I assume they mean on the core itself. That
mm,
might be a better one if you want to get back to this person privately in an email
yeah,
after the
I mean,
webinar.
maybe we can. Yeah, maybe we can. Maybe uh, take this one offline. I'm not sure about how mechanical because I don't know. I'm not sure what that means, but
Okay. This next question I think is a good one. Can the additive be used with a cold box system?
well, in this case, we done testing with the cold box system, and sorry, there's a noise on the background. I guess somebody's mowing the grass. So, um, yeah, we now done comparison of smoke suppression, testing with this additive in phenolic urethane Novec and cold box, and we already know now that we had to make adjustments to the blend to be uh, to be able to suppress the smoke at the same kind of level as we're doing for the PET set for the cold box. I think there's more a little bit higher smoke on the cold box, so we need to reformulate a little bit the blend to get us there. So we're working on that.
Okay. There's a few more questions, but I think you could take those offline as we've reached our time limit. And I just want to go to the last slide here. ASK wants to thank everybody for participating in the webinar today, and we have digital services available for you so that you can find our products faster and so that you can find technical data information on ASK's internet, or you can email our experts directly. And we will be having more live and on-demand webinars coming in the next couple of months. I think that wraps it up. Paul, do you have any last words you want to
No, I
say?
just want to say thank you for coming today and enjoy the rest of your day. Uh,
Thank you. Have a good day.
Thank you.